If you have worked with data intensive applications where the data is coming in from multiple data sources and you want to query that data in real time and mainly do analytics on top of it, and we are talking about billions of rows, multi billions of rows, right? So I'm pretty sure you might have heard of ClickHouse. But don't worry if you haven't, because we are going to talk about ClickHouse today. So, with this, I welcome you all to another episode of the Geek Narrator podcast. I am your host, Kaivalya Apte. And today, to talk about ClickHouse, I have Tom and Tyler from ClickHouse. And I'm really excited to have both of you. This is the first podcast actually that I have two guests. So let's see how it goes. I'm really excited. Welcome to the show. Thanks for joining. Let's start with a little bit of introduction about yourself, about your experience, and what you do at ClickHouse.
All right, then let's start with myself. Hi, my name is Tom. Thank you for having me here in the show. I'm a product marketing engineer at ClickHouse. My origin in computer science is I studied computer science in Munich, Technical University of Munich. Probably you can hear I'm German. I grew up in Germany. Then I spent 4 years as a database researcher in University of Tübingen, also in Germany. Then I started as a software engineer at Siemens in Germany, became a software architect. Then in this role, they sent me to a conference from MongoDB, and I was so blown away by this everything that I applied and started to work for MongoDB as a consultant and trainer. Then, interestingly, where I live right now, Elastic contacted me, and I spent the next 4 years working also as a consultant and trainer for Elastic. And then ClickHouse appeared on my radar, and as you will see in a bit, I was so blown away by it, by its performance, speed, everything, that I had to work for this company. Yeah, here I am.
So glad to have you here.
Awesome. And my name's Tyler. I look after developer advocacy at ClickHouse. I've had the fortune or misfortune, depending on who you talk to, of working in the database space for a little bit over 25 years now, either as a database administrator or as an engineer or in marketing or in community. And fundamentally, what I've found is that I like telling stories about the software that other people build. That's what I'm good at. I'm not a great engineer. I can make it work, but it's not my superpower. And so instead, I get to spend a lot of time talking about ClickHouse and the database space in general. And I think databases are really interesting, particularly in context of a podcast like this, because it's hard to talk about them without talking about the internals depth. And that's incredibly compelling for many of us. But I think the best way to understand ClickHouse in specific is to actually play with it a little bit. And so I encourage you to play with it a little bit, but I thought maybe it would make sense, if you're cool with it, if we started off this session by having Tom show us a little bit about ClickHouse.
Go for it, Tom. Let's see
Sure.
ClickHouse.
Great. All right. So I'm connected to a AWS EC2 box here, having 32 CPU cores, 64 gig of RAM, and I have started the ClickHouse database server, and I'm connected with the ClickHouse client to the database server locally on the same machine. And what I want to show you is what also blew me away, how incredibly fast ClickHouse is. And I'm doing this by creating a brand new table. This table has 2 columns, and I will fill this table with data. So the 2 columns are of integer data type, and you will see the semantics when I show you the query to put data into this. So I'm using the numbers, this table function that generates me 100 million numbers, integers starting with 0. And then I insert 100 million rows into this table. I use the actual number as the first column, and second column, I just generate a random number. Let's do this. All right, it took 2 seconds. Let's quickly double check that we indeed have 100 million rows in this table, and maybe select 3 sample rows. So this is my ID and this is my random number. So let's execute a query over this table with 100 million rows that is sorting the rows by this randomly generated value column. And I want to have the three smallest ones from this table. Okay, that took 3 milliseconds. What about getting the three largest numbers? So we order by descending. That also is 4 milliseconds. And so actually, what I'm doing here is a bit of cheating, because when we quickly go back to the definition of our table, I defined that X is a primary key, this random number, meaning that we store this data sorted on disk by this value. And ClickHouse does some internal optimization that we can discuss later in more detail, called read in order optimization, where it sees, okay, I can skip the sorting because I can just read the data and order it's stored on disk. And furthermore, I just want to have the top three. It can also just do a short circuiting. And the moment it has at least 3 rows read, but we are reading data in terms of blocks, we are actually reading a bit more rows, then it can just stop processing. Okay. Now, okay, let's sort by a column that is not part of the primary index or primary key. Let's order by this ID column. This is still pretty fast, 32 milliseconds. And when you look at the throughput, the processing throughput, ClickHouse on this EC2 box just processed roughly 3 billion rows per second. Okay, so what about aggregating this data? Let's say we want to calculate the average over this randomly generated values from the X column. And I use a convenient function that formats this in a human readable format. So let's do this. Yeah. And by the way, there is no index support. The only way to execute this is for ClickHouse to do like a full table scan, inspect each single row and create the aggregate value. Let's do this. Okay, not bad. 23 milliseconds. Again, it was 4 billion rows per second processing speed. Yeah, 2.15 billion is the average. We could also do the sum. Okay, 25 milliseconds, and it's a pretty high number, 214 quadrillion. Yeah, and again, 4 billion rows per second throughput. Then, okay, this was an artificial generated table that I just filled with 100 million rows. I also, as a preparation, loaded table data into this instance here, and it's from the ClickBench dataset. So we also have a kind of, from our side, official benchmark for data analytics stores called ClickBench, where we compare all kind of analytical data stores in terms of performance. And we are actually using a realistic data set from the origin of ClickHouse. So it was meant for analytics of click data, of internet, users browsing the internet, clickstream analysis. And ClickHouse also has an obfuscator tool. And so I have a table, long story short, with 100 million rows, presenting real world data distribution, just obfuscated. We can have a quick look at this table. So it has 100 million rows. Then it has, and this is pretty typical for ClickHouse use cases, it has above 100 rows. So, 100 columns. So it's a pretty wide table, but that's perfectly fine. We will talk later that ClickHouse is storing the data column by column. So if you only access in your query 3 out of this 100 columns, then it's not a big deal. And let's also, before I show you query speed, check the compressed and uncompressed size of this data on disk. So we have about 50 GIB of uncompressed data and 13 GIB of compressed data. All right, long story short, let's do a typical analytics query. So when a user clicks on somewhere in a website, there's also the operating system tracked. And here I calculate for all operating systems, grouped by operating system, the average display resolution of height and width. So over 100 million rows. It's a cold start here. Okay, that was 80 milliseconds and with 1.25 billion rows processing throughput. And my last query from this quick demo, we want to have per unique region. So we group by region the count of different users from that region. The top 3 ordered by count descending. And this takes 385 milliseconds. All right, I think that's all I have for now. So this is what just blew me away, this raw processing throughput of ClickHouse. So when I first played around with it like that, I couldn't believe my own eyes. And quite often you see tweets, or what's it called now, X messages of users who also have a touch point for the first time, and they're also just blown away by how incredibly fast ClickHouse is.
That is definitely mind blowing. And I am more curious now, and I'm pretty sure our viewers are also more curious to know about how is this happening, right? So we are going to dive deep into internals of ClickHouse. And I believe that for making such an amazing database to perform such nicely and in a resource efficient manner, there is optimizations required at each layer of the database, right? So we are going to talk about those optimizations as well. So as we do while talking about all other databases in this series, we'll start with the ingestion, right? So as we saw, Tom just ingested 100 million rows in the ClickHouse database. What is exactly happening right from the API when I'm calling or inserting 100 million rows or 1 billion rows or whatever the data size is? What is exactly happening? Take us through the API to the storage layer.
Okay. Maybe before abstractly, there are basically two ways to ingest data into ClickHouse. You can push it externally by, for example, using a language client, using HTTPS API. So you send insert queries containing raw data to ClickHouse. A second option is that you let ClickHouse itself pull the data from the data source inside. This is quite useful, for example, when you want to ingest data from object storage into ClickHouse. So you can insert it with a insert into select from query. This is how we call this. And then the ClickHouse server autonomously by itself is ingesting the data in a highly parallel way. We can deep dive into this later. I want to start with the way when you push data into ClickHouse. Also there are two different ways. What we had from the beginning, we call this now synchronous data inserts, meaning that you send an insert query to ClickHouse containing a bunch of rows. We generally say that it's good to have to batch your data client side in this case, that you can send 100,000 rows, you can send 1,000,000 rows, you can send 2,000,000 rows in a single query. That's no problem. That's actually quite good if you can do that. If you can't, then we also have asynchronous inserts where ClickHouse is doing the buffering server side, so to speak, for you, where you send data to ClickHouse. ClickHouse is putting it into a buffer first, and then based on specific thresholds, either when a specific amount of time has passed or when the buffer has a specific size, then the buffer is flushed and data is written to disk. Now, writing data to disk, we have different table engines. So when you create a table in ClickHouse, you also have to specify what table engine you want to use for this table. So we have native table engines from the so-called merge tree table engine family. And we also have a bunch of integration table engines, but this is not relevant for data ingesting. And so our native merge tree table family table engine has the same core idea as the LSM tree, the log structured merge tree. So meaning that we receive data, a bunch of data from an insert query in memory. We sort this data, we split it into columns, and then we write it to disk. So to give you a concrete example, let's say that we get one insert query containing, let's say, 2,000,000 rows. Then by default, there is a setting specifying the insert block size, meaning how many rows we write in one go to disk. And so when you send 2,000,000 rows, the default value is around 1,000,000 rows. So we split this 2,000,000 rows into two insert blocks, 1,000,000 rows each. And then for each block with 1,000,000 rows, we sort the rows by primary key columns. Then we split it into the individual columns because ClickHouse is a columnar database system. And then we compress these individual columns blockwise, block by block. And by default, we are using setstd. It's a quite heavyweight compression algorithm. And then we write, so to speak, each single column highly compressed into its own binary column file on disk. Okay, then in addition, we also, based on the primary key, create a primary index data structure. And here, this is quite special in ClickHouse because we are using a so-called sparse primary index file. This means that in contrast to traditional relational database systems, we are not creating an index entry for each individual row, for example, by using a B tree or B plus tree, because as you saw, we are optimized for ingest and query throughput, and especially for ingest throughput. That would mean that for each single row, we would need to add a new entry into the B tree, maybe even rebalance it. And also when we have one entry per row, the index would be quite large. And so for us, it's really important that the index file fits into memory. And because of that, we use so-called sparse indexing. That means we have our individual column files on disk. We further logically divide this data into so-called granules. And granule is just a chunk of consecutive rows. By default, one granule is containing 8,192 rows. And then for each of these granules, we create one entry in the primary index data structure, which is just a flat array file. And each entry, in each index entry, we just store the values from the primary key columns from the first row from each granule. And by that, we significantly reduce the size of our index. The disadvantage is that when you have let's say, a select query where you search for a specific row having a specific primary key value, we cannot immediately identify this single row. Instead, what we have to do, we can identify the granules, the block of rows that potentially contain a row with the specific value by just doing a binary search over the index entries. And then we scan the identified granules. And because we store the data ordered by primary key columns on disk, it's like a clustered index, just that we have the sparse indexing. This is quite useful for speeding up range queries that are typical in data analytic queries. Yeah, give me the revenue of the current month compared to the revenue from last month. So we want everything greater than a specific date column. And so this works really well with the primary index. Then I mentioned this part. Okay, so we got our insert query containing 2 million rows. We split it into 2 insert blocks. We split this into column files. And then for each insert block, we create a path on disk. A path is a directory containing this highly compressed column file together with per path, a primary index file. We have additional files. We have like column statistics, we have checksums, we also have additional index data structures like a secondary data skipping index. We can talk about this later. This is also stored per path. Each path is self-contained, and this allows us to have a really high write throughput, because when you think about it, you get an insert query and you don't need any locking for concurrent insert queries, because each insert query is creating completely independent, self-contained parts on disk that we just write to disk as fast as possible. And then later in the background, we merge these parts into larger parts to optimize for read time. Because I mentioned that each part is self-contained, containing its own index file data structures. That means when you later have a query over the whole data set of a table, and you have a lot of parts, the first step that we do is load all these index files into main memory, do the index analysis, identify per part the granules, the chunks of rows that potentially match our query. Yeah, and then we move this data into memory and process it. We will discuss later how we process this data. And so in order to reduce these steps, we later in the background, it's like an LSM tree, these parts are merged continuously. And so when we merge parts, can you imagine, because I mentioned that these column files, they are compressed. So what happens when you merge n parts? We load the column files from the parts into memory, decompress the data, merge sort based on the primary key columns. These columns recompress. We also create a new index file, and then we write a brand new part to disk. And the old parts, as long as there were still queries running over these parts, we keep them. And once we see that in our engine that there is no more references to these old parts, then we delete the old parts.
That's a great introduction to how ingestion works generally in ClickHouse. And I see there are multiple parts that are happening, and it looks like a standard flow when we talk about, okay, we are using LSM trees, we are using column oriented format to store our data. And I want to understand how the data is partitioned. When I'm ingesting, I define my primary key, like you just showed us. What is happening? How the data is distributed? Is it based on the primary key?
I know it's not based on the primary key. So what I talked right now about is how a single ClickHouse instance, a single server would ingest data. And you're right, ClickHouse runs basically everywhere on my local, here on my laptop, on a single EC2 box, but you can also deploy ClickHouse as a distributed cluster. And then data is distributed over the existing ClickHouse instances in terms of shards. That means the table data is split into distinct subsets of the data. And the splitting is not based on the primary key, but instead on a partitioning key. And so you can define existing columns, but it's also perfectly fine to just use a random number function. That means that then the data is distributed over the servers randomly, and by that, by definition, evenly. And then the data is stored, we call this shards, over different multiple nodes. And then typically you use a distributed table engine. That is just like an abstraction over this splitting of the data that allows users to use a distributed setup like a single node setup by sending their queries without mentioning any sharding key to this distributed table. And the distributed table has knowledge about how the data is distributed over the existing servers and is then forwarding the servers to all to be involved servers that are executing the query locally, are streaming back a local result to the initiator node, or the initiator node having the distributed table. And the distributed table, this node is then calculating from the local sub-results the overall global results and then streaming it back to the caller. This is the classical way, but nowadays it's quite modern to separate storage from compute. For example, to store all the data shared in virtually limitless object storage. And then all cluster nodes basically have access to the same shared data. And by that, more behaving, we didn't mention replicas yet, but they are behaving like replica nodes. Let's maybe quickly talk about replicas. So in a distributed setup, sharding is meant for scaling your setup with the amount of data. For example, if the amount of data doesn't fit onto a single node, then you can split it into shards and distribute it over multiple nodes. Or you can use this concept in order to speed up execution of a single query, because now instead of a single server executing the query over all the data, n nodes are executing or working on the same query over one end of the overall data. And you can also create replica nodes for all the shards, and replicas are one-to-one copies of shards, and they are meant for high availability. So if one of the nodes holding a shard is down for whatever reason, then all the shards are still available to receive writes and reads, because there will be another node holding a replica. And now when we go back to this modern separation of compute and storage architectures, well, I mentioned if we store all the data in object storage, then we have a bunch of nodes seeing all the same data. Then when you think about it, logically, they are more like replicas because they all see the same amount of data. So they are like virtual replicas because they don't really store data by themselves. And for this scenarios, we have a second mechanism called parallel replicas. It works similarly to what I mentioned about distributed table executing a query over multiple shards. Here we have also an initiator node, so that's just the replica or the ClickHouse instance that by accident receives the query. This is then forwarding the query to all the existing replica nodes and orchestrating the assembling of the overall result and streaming it back. It works in the same way, but is more tailored for modern separation of storage and compute architectures.
And I think what Tom just described is actually pretty intriguing from a distributed systems standpoint. Yeah, I spent a whole bunch of time in the NoSQL era arguing about consistent hashing versus other approaches to sharding and replication, manual sharding, dynamic sharding, etc. Fundamentally, what I've found and what's been interesting for me in talking to ClickHouse users is people tend to scale up before they scale out. And one of the side benefits that I don't think, at least to me, having spent so much time thinking about distributed systems, that wasn't like obvious, was when you have amazing compression, when you have very high performance, and ClickHouse is written in a sort of C++ and a bit of assembly, when you're not constrained by the JVM, you actually have the ability to throw hardware at the problem before you look at how you shard. Having looked at that, I think what becomes very interesting is this pattern that we see of scale up before you scale out. And then there's the other pattern, which is how am I able to, rather than scaling out, separate storage and compute so that I can operate in a more cloud-friendly, if you will, style pattern than if I was owning colos or running in traditional managed service data centers. And it's a bit of a different mindset when you approach ClickHouse to think about, I'm going to get as much data onto one thing before I start distributing across many things.
That makes sense. And when we talked about having these different models of storage, right? Like one is where the compute nodes also store data, and then you have replicas. And then the other one where the compute nodes are just talking to the storage system, which is a distributed object store. And they are basically stateless. They are just consuming data from the storage engine or the storage system, which is an object store, maybe an Amazon S3 or something. Does this exist already in ClickHouse? Let's say my data is already in S3, right?
Mhm.
And I want to just have ClickHouse as my compute engine and use S3 as my storage. So is it still possible? Is it possible now? Or I have to run ClickHouse in this traditional way where each ClickHouse node in a cluster also has the data?
No, it's absolutely possible, actually, in two ways. So one way for if you just do an ad hoc analysis of this data that you already have in, and by the way, this is also something quite nice with ClickHouse. We can pretty much read any format that you can think about. We can also write into any format that you can think about. We can export data. And so when your data is already living on S3, you can either use one of our so-called integration table engines that I briefly mentioned before. We have an S3 table engine where you can just ad hocly query data stored in S3. The disadvantage is that you don't have index support in this scenario. And what you also can do, you can create a shared merge tree table backed by S3 storage. And then you can use the integration table engine to read the data and then write it into our native format, so to speak, with a full index support, the format that I mentioned before. And then, you have a merge tree table engine backed by object storage.
That makes sense.
Then, yeah.
And so to build on that real quick, I think the concept of a table engine and table functions generally are something worth just touching on briefly. Fundamentally, our belief is that a database is only as good as the data that's in it or the data that's accessible to it, right? The best database without any data is meaningless. It's like a network without any users, right? And so Tom spoke about this concept of table engines. We talked briefly about merge tree, about replacing merge tree, about summing merge tree. And those are the contextual ones that you tend to think of. Those live in the merge tree family. Then there's a series of integration engines. And this is really where some of the beauty of ClickHouse lies, is if I want to access data via ODBC or via JDBC or via MySQL or Mongo or Redis or HDFS, Kafka, I'm sure there's other, Postgres. Postgres is, of course, a very obvious one. And S3 being another, and also S3Q. I have the ability to not only do read and lightweight analysis on, but I could also use that as the integration point to get data into the columnar structure of ClickHouse as well. So to your question there, that's the way of getting that data that lives elsewhere or away. beyond the sort of write pipeline of getting that data in and being able to really design an architecture that matches the needs of whatever the environment is, rather than being tied to you must deploy 5 nodes, you must have one coordination node, or it only runs on a single instance. Whether you're running ClickHouse locally on your laptop or in a massively distributed cluster with the separation of storage and compute, the interface for the operator feels largely the same. The tasks change, but it's just ClickHouse. And that's important because I can take Tom's data set of clickstream data and I can interact with it here locally in an ephemeral instance of ClickHouse local, or I can log in to the server that he just showed, or we could deploy that to a massively distributed cluster, and the experience for the analyst remains the same.
So also in a typical ClickHouse way, as fast as possible, highly parallel. When you want to read data, for example, from object storage, we also have extensions of these table engines or table functions with a cluster postfix. So we have an S3 cluster table engine or an HDFS cluster table function. And what that allows you is that you can involve all the nodes in your cluster. When you have a 10-node cluster by accident and you want to read data as fast as possible, highly parallelized, then you can utilize this cluster version of this function. And when you have a lot of files on S3, then ClickHouse automatically and dynamically splits these files over your cluster nodes, and then each of your 10 nodes in parallel processes a subset of files. And again, when each of these nodes, let's say, has 32 CPU cores, then it's also for the local set of files that the server needs to process, it's also utilizing all these CPU cores for parallel insert threads, and each insert thread is responsible for regions within the files. And so you can see you can ingest data or access data from external systems in the ClickHouse way extremely fast.
That makes sense. And just to go back to the ingestion flow and talking about the distributed cluster deployment, for example, where you have multiple nodes of ClickHouse, and then you define a partition key where you want to, and it can also be a random ID, right? And it can go to, based on that partition key, it can go to a specific node. Of course, there will be replicas and all that. And then there is a primary key. But of course, my partition key can also be my primary key, right? Because it's just a different way of defining things. Coming back to single machine, because there we started. Once I have the data on the machine, you mentioned 2 modes, which is client can use buffer or batch the data and send it, or the server can also buffer and write it to disk. And then you also mentioned that how the data is split into granules and stored on disk. And then there is columnar format, of course, because it's OLAP and you want compression. You also mentioned about how the compressed data size and uncompressed data size looks like in your demo. So that is all interesting. I'm curious about the granule size though. So you mentioned 8192, if I have written down correctly. What are these? These are number of rows. What is 8192 and how did you come up to this number?
The number is pretty random. It's just in the past, we saw that we get good performance with that. And actually, nowadays, ClickHouse is doing these granules not necessarily based on amount of rows, but dynamically based on a max size. For example, you can have granules that are 1 megabyte or 10 megabyte max in size. And so it can, if you have some rows with columns that are where the values are larger than from others, then it's not necessarily 8,192 rows per granule. It's just our unit. You can, maybe it makes sense to explain it from indexing perspective. So the granules is just a logical division of data, and it's the unit of index access. So each granule is indexed, and the larger your granules are, the less entries your primary index file will have. The smaller you make these granules, the more entries you will have. And the more likely you can, in an extreme case, you could have a granule size of 1 row, and that this would reflect traditional indexing, where you have 1 index entry per row, but the index size would be super large. So it's a trade-off that balances size of index files in memory with processing speed.
Okay.
And if you want to, if you or a listener wants to dive into the architecture and some of the options in greater detail, I think the thing you'd search for in the ClickHouse docs is adaptive index granularity. Fundamentally, as Tom said, think of a variable n, right? If n is less than 8,192 and the size of that combined row data is less than 10 meg, which is the default, that's when you roll over. But the index granularity byte is configurable. These are just the defaults we've found that work well for the vast majority of use cases. From an optimization and tuning perspective, that's not one of the first places to go and tweak.
Interesting.
So I want to add that this is the unit of indexing and index lookup. But actually, when we later talk about query processing, this is not the smallest unit of how we move data from disk, from storage into memory. Actually, the unit blocks. And so we have a block default processing block size. So normally, once we identified granules, we are primary index lookup that we want to move to memory for further processing. Then we don't do this granule by granule, but we do it block by block. And we have a default block size of around 65,000 rows. And this number stems from optimizing for CPU level caches. And so this is the unit of data processing. We identify granules that are of interest for processing. Then we move blocks that contain these granules, contain consecutive granules into main memory, and then we process data.
Interesting. Okay, that makes sense. And I before we go on to reading data, because we have to close the loop, I want to understand ingestion from a different perspective. So let's say I'm a small company and I want to use ClickHouse. I've been doing business since 10 years now. And I also want the historical data being stored. And let's say I have data in my Postgres, I have also data in my S3. And along with that, I also have data coming in real time, because now I'm a big business and I have ton of events coming in real time. Now I want to onboard onto ClickHouse, right? How would ingestion look for me? Because now I have 3 data sources. One is historical and 2 are real time and 1 is historical. How does that kind of merging of data happens? And when I say historical, it may not be like only 10 years old. It can also be like, I don't know, 10 days old. So this is just an example. So what happens if I'm getting the real-time data and I also have historical data? How does this ingestion happens, and how does it combine data to serve the queries?
Yeah, so I would advise you to keep both real-time data and historical data in ClickHouse. How to do that, I will explain in a bit. But we also put federated queries by using the already mentioned integration table engine. So it's perfectly okay to formulate a query that joins local data, so to speak, with remote data by using a MySQL table engine, Postgres table engine. And you can combine data from different data sources locally on your ClickHouse instance. But what I would recommend is and this is also one of the main ingredients for query performance in ClickHouse, and many of our customers are using that. I would recommend you to use materialized views to generate the historical data. To give you an example, maybe you get real-time data with granularity once per second you get in your data item, and maybe data that is older than a specific amount of time you want to just pre-aggregate. Maybe you want to have aggregates per month, the amount of unique visitors per month. And you can do this in real time in ClickHouse without influencing ingestion throughput by using a materialized view and by using a specialized member of the merge tree table engine family. For example, we have an aggregating merge tree table engine, and you can define a materialized view together with a target table from the aggregating merge tree engine. And when you do that, when you get new data ingested, like I mentioned before, you get an insert query with a bunch of rows. Then these rows are stored in your original, we call it, let's say, source data table, in your raw data table. And at the same time, the same block of rows is handed over to the materialized view, which is just a transformation query that you can define, where you can already group this data, maybe by month, and calculate aggregations. But in order for this, we call this automatic incremental data transformation. In order for this to work correctly, we need to store not the actual aggregation value, but an aggregation value state. For example, when you think about you want to calculate the average, we need to, instead of storing the final average, we need to store the current sum and the amount of values that we saw so far. And we store, like I said, in parallel, the data that you received also into an additional table of replacing merge tree engine type. So we also write regular paths to disk. And you define also a primary key for this additional table. And in the background, incrementally, when we merge these parts together, then all rows who have the same primary key values, they are merged into a single row, and we apply the defined aggregation function. So for example, for an average, you have two rows with the same primary key value. In one, you say the current average is 4, stems from two values. In the other row from the other part, you have a row also 4, stems from two values. So then we merge these into a new part, and we save the value 8 stemming from 4 values or something like that. And by doing that, we incrementally in the background, during background merges, just by using a specialized merging algorithm, incrementally aggregate data while still containing high ingest throughput. And so at the same time, you have your most current raw data, for which you also can define TTL rules. You can automatically delete this data because you already have this data condensed, pre-aggregated, and keep it for longer.
Interesting. I have two questions. First, we have been talking about merge trees, right? And we have also already mentioned different types of merging trees: aggregated merging tree, summing and replacing, and traditional merge tree, or averaging merge tree. Let's talk a little bit about these merge trees. So from a user's perspective, right, while I'm ingesting data, should I care about understanding these merge trees? Which one should I use? Or this is automatically taken care by ClickHouse depending on what kind of queries I'm going to run on top of it?
I have two answers for this. So in the meantime, we have a way more abstract version of this mechanism that I just explained called projections. For a table, you can also define a projection that behaves almost like a aggregating merge tree with a materialized view. So whenever there's new data, we store the data in the original table, and then in the background in a different form, maybe pre-aggregated or even with a different sorting order in order to have a different primary index. We store it in the background in additional tables. And the advantage of a projection is that this is all transparent for you as a new user. You can just send a query targeting your original table. And if it's an aggregation table with a group by, applying an aggregation function, and we have a matching projection, a matching version where the data is pre-aggregated, then we run this query on this version, on this table instead. The same when you define projections with different primary keys in order to speed up queries filtering on other columns that are not part of the primary key of your original table, then ClickHouse also transparently looks if there is a better version and executes the query transparently this kind of table. So this is one version of this answer. The other is if you want to use materialized views, and there are also advantages or disadvantages, pros and cons compared to projections, then yes, then you need to know about how replacing merge tree engines work. And summing merge tree is just a specialization of a aggregating merge tree table engine. And so these are the basic two table engines to pre-aggregate your data in the background. What you mentioned, collapsing merge tree table engine and also version collapsing merge tree table engines. These are two table engines to implement updates in a kind of ClickHouse way and in a very performant way. So instead of, we didn't mention that these paths that we create when you ingest data, they are immutable. Yeah, we just write them to disk, we merge them in the background to larger parts, but you cannot modify, update rows that you have in a specific part. and then this would be too slow. And in order to implement updates as fast as possible, you can use a replacing merge tree table engine, where, again, based on the primary key, we again do this in the background at merge time. Imagine you have a row existing with a specific primary key, and now you want to replace this. Instead of updating this row, you just insert the new row with the updated values in the other columns. So we write a new part to disk. And then later in the background, when we merge these parts, we keep only the row for when we have more rows with the same primary key values, we only keep the latest. And so the update takes place asynchronously in the background. And there are, you can also imagine that in a real-time system where you get constantly new data, this merging is never finished. Yeah, there will be always be cases where you still have parts with the old data. So what do you do at query time? We have a special keyword that you can use then. It's called final. And then we do this merge logic from the involved engine of your table that you query also at query time to get rid, so to speak, at query time in main memory of replaced rows. But I also want to mention this. In the meantime, when you want to update data, in the meantime, we have other mechanisms. You don't have to use this collapsing merge tree mechanism. It's still valid to use it because it's very efficient to do it like that. And the modern way is where when you update data or when you delete data, we mark them as updated or deleted in their corresponding parts. And then at query time, we just fetch the most current version of a row, or we ignore the deleted ones. And again, at merge time, all the rows that are marked in the past as updated or deleted, they will then not be part, or just the updated version of a row will be part of the merge part when we merge in the background. So technically, it's still the same as if you use a collapsing merge tree. It's just easier for users to understand when they use this update mechanism on the original merge tree table that they use.
I think the only one Tom didn't mention, just for the sake of completeness, is the graphite merge tree, which if you're storing graphite data, you might care about a bit. Fundamentally, merge tree as a table engine is the default table engine in ClickHouse, and it is applicable to a wide variety of use cases. It's when you have that set of real-time data, plus your historical Postgres data, plus some data stored off in S3 somewhere, and you're pulling them into ClickHouse, and you're really beginning to optimize what your queries look like, that you dive into materialized views and projections, and should I look at aggregating merge tree for this specific set of business analytics that I'm doing? The way that I would say 90% of our users start, because it is the default, is to start with merge tree and to learn from there and let the data influence the decisions that you make, rather than having the database architecture define the decisions that you make.
That makes sense. That does make sense. So for, as you mentioned, for 90% of the customers or use cases, the default merge tree sounds good. But when you have specialized use cases, for example, just taking an example here, if let's say I have a lot of updates and deletes as well, and it's pretty heavy. So probably I want to dive deep into version collapsing merge tree. So I get this MVCC style merging where there are multiple versions, but you eventually get the latest version. So that could be one use case. But 90% of the use cases, the default merge tree should work. And if it doesn't work, of course, there are more optimizations like different merge trees that Tom and Tyler explained, right? Is that a good summary or?
Yes, but I would add that the scale of data that our customers typically have, we are talking about billions of rows and petabytes of data. Almost all of these customers use either projections, aggregating merge tree, because typically analytic queries are grouping and calculating aggregates and sorting this data.
Yeah.
And this can be significantly sped up with re-aggregating the data asynchronously in the background. And the resulting tables are contain significantly less data and still allow millisecond queries over this data or sub-second.
Okay. Yeah, that does make sense. You mentioned a bit about the pros and cons of having a materialized view. What are these? So is it just more storage is required because you're pre-aggregating and you're keeping like an aggregated value as well? Or what are some pros and cons that users should keep in mind?
Yes, we can also mention projections. So in terms of additional requirements for data storage, they are both the same, because with both we create additional copies of your data, just pre-aggregated or differently sorted. This is one con, that you need additional storage. But when we talk about, let's say, aggregating merge tree, based on your granularity, if you aggregate data per month or per year, typically we are talking about tens of megabytes, even for petabytes of original data. So it's not significantly. Another con, of course, would be that when you have materialized views with this additional target tables, with a materialized views, this is quite explicit, meaning that you need to decide in a query, to which table do I send this query to? Select from, you need to decide, okay, this query is for this materialized view. When you use a projection, like I mentioned before, this is completely transparent. You always send the query to the original table, and then ClickHouse is doing index analysis on all the different table versions that it has, and then chooses the one that would cause the least amount of data to be read and processed. That's already like a con pro. Projections versus materialized views. Yes.
Okay. That sounds good. I think it's time that we move to the query side where now the ingestion is complete. Of course, we have talked about aggregating merge trees and replacing merge trees and different types. I guess the understanding of how the query processing is done would be simpler. Let's start with, so let's say I have ingested, as you mentioned, 100 million rows, and I want to run analytics. So we talked about partition key and primary key so far, but let's
Mhm.
say I have to run queries on different columns. How do I specify that these are my columns that I want to query on to get better performance?
So first of all, ClickHouse uses standard SQL. Here you use a regular SQL query, and it's the default technique of when you filter frequently on, let's say, column A and B, then you will get a significant speed up if you use a compound primary key containing columns A and B, because then, like I said, first of all, we sort data by these two columns, and then we create index entries for the granules, containing for each granule the values from the first row from these primary key columns. And by that, when you have a query filtering on these columns, we can just do a binary search over the index entries, identify the granules that potentially contain matching rows, and then stream this into our query processing engine, and then, check if actually these rows match your predicate from your query. So it's always a default technique to have a good primary key for your queries. And if you have conflicting requirements, because one kind of disadvantage of this sparse indexing based on physical sort order on disk is that the table only can have one primary key, because there can only be one way to physically store the data sorted on disk. And so if you want to have queries fast that filter on column A and B, but you also want to have queries fast that filter on column C and E, then you can use a projection or materialized view to automatically store whenever there's new data ingested. You also store this data differently ordered on disk in a second table behind the scenes in a projection and explicitly when using a materialized view. And then with a projection, you don't have to do anything else. So it will automatically speed up both kind of queries, filtering on A and B and C and E. With a projection, again, you need to explicitly then send the second query, filtering on column C and E, to the materialized view or the target table of materialized view.
That makes sense. So basically, it boils down to knowing what I want to query on, right? If I don't know my queries, I cannot optimize. It will be the default performance that I get. But if I know my
Ye-
queries, I can create materialized views or projections and create my primary key. That makes sense. Tyler, did you want to add something?
Yeah, I was basically going to say exactly what you just said, which Tom and I often end up talking to different classes of ClickHouse users, right? Whereas he's talking to the power users. I'm often talking to people who are trying it for the first time. And I always point them to this fantastic article on the ClickHouse blog called, I think it's called Supercharging Your ClickHouse Queries. It was one Tom actually wrote about this time last year. And he makes a statement at the beginning of it that's queries are typically fast enough, but every millisecond matters. That's something we believe strongly at ClickHouse, is that every millisecond matters. And when every millisecond matters, then there's a series of steps you can follow to like improve that query processing time, about using proper primary indices, et cetera. But that article slash paper, if you will, white paper, actually walks through, hey, how should I think about primary indices? How should I think about pre-computing aggregates? How should I think about views and projections? When the milliseconds that you're spending are more milliseconds than you choose to, there are all of the knobs to tune, which I think is one of the cool things about ClickHouse. Is you can often, I talk to people who are like, Postgres doesn't scale, I need help now. And I'm like, cool, ClickHouse can help you now. And then they have immense amount of data and they're like, okay, how do I make it even better? And it's great because it supports you in that journey from, I'm just going to ingest data and try it, to I'm going to actually optimize based on knowing the internals of my data deep.
That sounds good. I'm going to add that link to the blog so viewers can definitely give it a read and understand it more deeply. And this does make sense, right? Because if I don't know my query, I'll get the default performance. And if I'm at that level that every millisecond is mattering, I know my query already. So I know how to optimize that. And as you mentioned, there are multiple settings and knobs and configurations that I can tune to get my query performance up to the mark. There are two workloads happening, right? Like one, rather three workloads. So one, there is ingestion and real time that is happening. Millions of rows are being ingested. Then there is a lot of processing happening on the background. There's a lot of merging happening. Projections are updated and all that. And then there is also read queries. How does ClickHouse separate these workloads? And as a user, do I have to think about it? Do I have knobs too? Let's trade off my ingestion performance with slightly better read performance or something like that.
Yes, so ClickHouse offers so-called workload isolation. So when you want to isolate a set of queries from influencing the performance, let's say, of your most business critical queries. And so we have different settings to restrict the amount of CPU cores, or later when we talk about query processing, the amount of threads from a thread pool that a query is allowed to use to keep enough cores or threads available for your main queries. The same for memory. You can define flexible memory limits. And so ClickHouse checks if there is more memory available than you configured for a set of queries, then they are allowed to just use that. But the moment one of your mission critical queries runs, we guarantee that they can also use their defined amount of memory by limiting the flexible defined memory limits for the other sets of queries. And you can also, this is quite a new feature, you can also define limits on remote disks in terms of how much resources we use, also in terms of threads to read data. So you can control CPU, memory, disk, and also network I/O by that per group of queries, so to speak. We call this workload isolation.
That is great. And this again, maybe does not apply to 99% of the use cases, but when there are some use cases, let's say power users, when they really want to go deep into optimization and all that, I think this might be useful, right? So knowing this setting is pretty useful for some of the workloads. This is cool. And I know there are two offerings. Like one is definitely it's an open source database, and then there is cloud offering. Did we talk about anything that is not part of open source, or you want to? Okay, perfect. Then what is additional that I get when I use cloud offering?
Okay, so first of all, table engine, tailored, engineered from the ground up for cloud architecture, separation of storage and compute. We probably don't have enough time here in this context to explain the kind of disadvantages of the existing replicated merge tree table engine for modern cloud architectures. But yeah, you get a cloud native table engine that fully supports this horizontal scaling where you can add just new compute nodes, and both your ingest and your query processing will be ideally linearly sped up by doing this. I would say this is the main advantage. And of course, you don't need to deploy, configure, manage your ClickHouse service. We do that for you behind the scenes. We have, okay, this is also pretty important. We have automatic cluster scaling, both horizontal and vertically. So based on memory pressure and CPU usage, we automatically increase the size of compute nodes. Yeah, but by just dynamically using more cores and more memory, we just behind the scenes switch the size of nodes. And also, what I just mentioned, you can add additional nodes and also reduce the amount of nodes based on your workload. I would say that are the main advantages. Maybe Tyler has more to offer.
Yeah, no, indeed. Those are the main things. And again, there's a fantastic blog we wrote that talks a bit more about the concept of shared merge trees. You might find out if you play with ClickHouse much at all, we tend to write a whole lot at a deeply technical level. I'd say the other addition is Tom spoke briefly about the deployment model. We often refer to it as a serverless style consumption, in that I'm defining upper and lower bounds, which is really great for those bursty workloads that tend to be like daily batch jobs, so that you don't have to keep a whole bunch of spare capacity living around and paying for it when you don't actually need it. So it tends to be a very good price to performance ratio. Of course, because we're running it, you don't have to. So there's an operational benefit, but that's a very common sort of cloud story. It is SOC 2 compliant if security matters. And then the other thing is there's a really cool SQL console that hangs out in cloud. If you're using open source ClickHouse, there's this fun thing that ClickHouse Play. That's a lightweight console, but we do have an interactive console with a table explorer and a query interface and some actual ChatGPT integration if you've broken your query and don't know how to fix it. But fundamentally, from a cloud perspective, it's just fast and easy. And I think that's a consistent story for almost all cloud deployments is simplicity, speed, and cost.
Sounds good. Let's talk about the use cases and the future. Of course, so we talked about analytics as a use case, and I want to do real-time analytics. And we also talk about the different deployment models. You can use it on a single machine. You can also use it on a cluster. What are the interesting use cases that you want to highlight when it comes to, customers that are currently using ClickHouse or at least evaluating ClickHouse?
Yeah, maybe I start. The typical use case is real-time data analytics, where when at the same time you get a high amount of new data ingested, plus you want to have super fast analytic queries, second range, millisecond range. Cloudflare is quite a famous use case for that are customers of us. They ingest 12 billion events per second, get 75 billion events daily. They know about the customer I cannot name in Europe who has tables with, this is real, 3,000 and more billion rows, so 3,000 billion rows with up to 6 billion rows added daily in real time. Yeah. Maybe Tyler is.
Yeah, absolutely. I think generally there's a couple of categories of use cases, and the real-time analytics one is definitely an important one. And it's a genesis of where ClickHouse came from, right? ClickHouse, Clickstream, Data Warehouse, right? The other one that we see, there's really three others where we're beginning to see a lot of growth. Logs, events, and traces, whether that's, hey, Elasticsearch isn't scaling for me and I want to look at something else, or Darwinium has a really cool story about how they're using us. We actually use ClickHouse for our own logging and tracing against ClickHouse Cloud. So we're seeing a lot of people begin to look at observability more broadly in context of using ClickHouse as a backing store for it. The other would be more of the analytics that's not necessarily real time, but is super meaningful. And you can think of that as like business intelligence-y kind of thing. And fundamentally, the way that I conceptualize it, even though it may not be appropriate, is if I want it in a dashboard right now, it's real time. If I want it in a dashboard in the last week is fine, then it's more business intelligence style. And then an emergent one that I'm really excited about. I mean, we have some great users, DeepL, AdMixer, among others, is really using ClickHouse as the backing store for machine learning and Gen AI work. There's a reason that we added vector search capability into ClickHouse. And fundamentally, all of those models are based on there's a giant set of data that I need to interact with. And one of the things ClickHouse is super good at is there's a giant set of data I need to interact with. So those are really the categories of where we see it. Usually when we're talking to users who are new, they either have this like beautiful greenfield idea of, hey, I'm going to build the world's biggest end, and so I need to scale, or they're like, we built a really cool thing and the database we used for it doesn't scale. And not to pick on a database, because it's actually honestly my favorite database, Postgres. We see a lot of people who are like, hey, Postgres is great on my OLTP side, but it's just not scaling on the OLAP side. I think perhaps one of the more canonical use cases of that for us is PostHog. As PostHog Cloud began to take off, they're like, this isn't scaling for us. And they made the migration from Postgres to ClickHouse. And that's really the areas where we see it, is in those buckets of effort, but it's usually either I'm going to build something that's amazing, whole stack of observability platforms that leverage ClickHouse in the back end, or what I have now doesn't scale and I need to solve the problem quickly. And that's when ClickHouse is often a great solution. Does that make sense?
It does. It does. It's really interesting to know all these use cases. What's in the future? So what is not there yet, but that, okay, there is more and more increasing demand when it comes to using ClickHouse for specific use cases?
Recent feature, for example, that is currently experimental is a full text search index, like an inverted index. We have more and more customers who want to keep all the data in ClickHouse and also use it for full text search. Then modern vector search use cases, large language models is all over the hype right now. We are working on specific indexing techniques to speed searching for vectors in a vector space up.
I think some other good ones are, from just a feature perspective, particularly on the open source side. Keep in mind what we develop in open source, where appropriate, gets deployed to cloud as well, which is awesome. Feel free to hit up our GitHub if you're listening to this. We always have a roadmap issue open. And we're always incredibly aggressive in terms of what we hope to accomplish in a year. Some of the ones I'm super excited about, and then I'm going to answer the question a little more esoterically. I'm super excited about refreshing materialized views. That's a thing that is often very requested and something people come for. Our JSON support, we've had experimental JSON support for quite a while. And Alexei just shared this on our most recent release call. We have a monthly release call with the community with Q&A. It wasn't scaling the way we wanted to. And so we thought of another approach and idea for it. And I'm super excited about. Generally, sort of at a higher level, I think for those of us who've lived in the database space for a really long time, we've seen this motion through the NoSQL era and through the emergence of incredibly cool cloud data warehouses like Snowflake and others, of beginning to bundle everything together. Like, we are the database for all your workloads. I think generally we're beginning to see people unbundle now and use the tool that makes sense for the use case rather than just using a tool for all of the things. Tanya, who's our VP of product, just wrote this, again, Tyler talking about blog posts, wrote this really cool blog post that she called Unbundling the Cloud Data Warehouse. And I think that it's affecting all of us in the industry as we think about like the data warehouse being like, I'm going to just throw everything there and figure it out later, to, hey, there's this category of real-time data warehouses and they solve a specific need that the traditional cloud data warehouse maybe isn't. I think we're going to see a lot of not only product features, but also like how we talk as technologists and as industry change over time as we begin to adopt tools based on what they provide rather than just based on the fact that we signed an agreement for them at some point in the past.
That is very interesting. And I'm really looking forward to the future, what's there in ClickHouse and its use cases. This has been really insightful. And of course, we don't have unlimited time, so we can only talk about these important things. But I personally have learned more about ClickHouse, and I am really curious to learn more by reading your blogs. And I do recommend our viewers that they also do the same. So I'm going to attach all the links that are relevant to ClickHouse so people can learn more, play more with ClickHouse, and feel the power of ClickHouse when it comes to performance and resource efficiency. So thank you, Tom, and thank you, Tyler, for being here. It was amazing to have you both. And I look forward to collaborating more on ClickHouse topics in the future.
Amazing. Thank you so much.
Thanks.